Welcome back. At first, Happy Teachers' Day. My pronoun and respect to all my teachers, Gurudev, my parents, and today's video I have dedicated all my teachers. Okay? Welcome back. Today's goal of this lecture. Today I will see one example which had come GATE 2022 exam. This is based on ring theory, but by this example actually I will review my previous theorem based on this question. Actually today's part is actually the reviews part by this question. At first let's see the question. Let Rx denoted the ring of polynomial in X with real coefficient. Then the quotient ring Rx modulo x to the power 4 ideal generated by x to the power 4 plus 4 is option 1 is a field, option 2 an integral domain but not field, option 3 not an integral domain but 0 as an only nilpotent element, and option 4 a ring which contains non-zero nilpotent. Here fx equal to x to the power 4 plus 2, the ideal generated by x to the power 4 plus 2, we can write this as factor of two irreducible polynomial x square plus 2x plus 2 times x square minus 2x plus 2. Since we can write x to the power 4 plus 2 to product of irreducible factors, so obviously this fx is reducible polynomial. Just recall the theorem. If R is a commutative ring with unity and if M is maximal ideal of R, then the quotient ring R mod M is a field. This is the if and only if condition. If R mod M is field, then M is a maximal ideal. Also, if M is a maximal ideal, then we can tell R mod M is a field. So this is the if and only if condition. If R mod M is field, we all of us know every field is an integral domain. So R mod M is an integral domain. And since R mod M is an integral domain, that implies M is a prime ideal. In a commutative ring with unity, we all of us know every maximal ideal is a prime ideal. But converse is not true, we all of us know, because in Z, every maximal ideal is a prime ideal. But if we consider the ideal generated by only singleton element 0, this is prime ideal but not be maximal ideal. So in a commutative ring with unity, every maximal ideal is prime ideal, but every prime ideal, not necessarily this is maximal, may or may not be true. Zx modulo ideal generated by x square plus 1, we can write this is as fx plus ideal generated by x square plus 1, where this fx belongs to zx. That means this fx equal to a0 plus a1x plus a2x square up to an x to the power n dot 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 plus ideal generated by x square plus 1. Okay, where obviously this ai belongs to integer. And notice x square plus 1 plus ideal generated by x square plus 1, this is equal to, we can write 0 plus id, because x square plus 1 would be included in this ideal. So this is equal to 0 plus ideal generated by x square plus 1. And by this equation we can write x square plus 1 equal to 0. That implies x equal to plus minus I. Here zx by x square, zx modulo x square plus 1, this is equal to the set containing, since x equal to plus minus I have got, so this would be set containing a0 plus a1i plus a2i square up to a to the power n I to the power n dot dot plus ideal generated by x square plus 1, where this ai belongs to integer. And obviously this is isomorphic to zi, which is integral domain. So since zx modulo ideal generated by x square plus 1 is isomorphic to integral domain, that means this is obviously prime ideal, but zi is not field. So this is not maximal ideal. Okay? Oh well. But if R is a finite integral domain with unity and M is a maximal ideal, then always R modulo M is field. This is integral domain with unity. Since R is a finite, so R mod M would be finite integral domain, and every finite integral domain always imply this is field. So if and only if condition, this is also when R is finite, and since this is isomorphic to finite integral domain, so that imply M is a prime ideal. That means in a finite CRU, an ideal is maximal ideal if and only if the ideal is prime ideal. Also, we all of us know, if F is a field and Px belongs to Fx, be any polynomial, then Px is irreducible if and only if Fx modulo ideal generated by Px is a field. If Px is irreducible polynomial, then that imply Fx modulo ideal generated by Px is a field. That means if Px is irreducible polynomial, then always Fx modulo Px is field, and if Fx modulo Px is field, then that imply ideal generated by Px is maximal ideal. So F is a field and Px belongs to Fx, be any polynomial, then Px is irreducible over F if ideal generated by Px is a maximal ideal. Also, if the ring is PID, that means we all of us know PID means every ideal generated by single element, then every prime ideal always be maximal ideal. Every prime ideal is a maximal ideal. We all of us know maximal ideal always be prime, but in PID converse is true. Every maximal ideal, every prime ideal is a maximal ideal. Our original question. Since Fx is reducible, so Rx modulo ideal generated by Fx, since this is reducible polynomial, cannot isomorphic to field. So option 1 is a wrong option. So option 1 is a wrong. We all of us know these rules. If R mod Ij, where I and J are co-maximal ideal of Rx, then this is isomorphic to R mod I cross R mod J. Here I equal to x square plus 2x plus 2 and j equal to x square minus 2x plus 2. This is isomorphic to R mod x square plus 2x plus 2 cross R mod x square minus 2x plus 2, where this is I and this is J, where x square plus 2x plus 2 is irreducible polynomial of Rx. Similarly, x square minus 2x plus 2, this is irreducible polynomial of Rx. So this is the co-maximal ideal, and Rx modulo x square plus 2x plus 2, this is isomorphic to C. Also this is isomorphic to C. This is isomorphic to C cross C, and we all of us know C cross C, this is not be integral domain because this is not contain zero divisor, because one zero zero one contain 0 0, but 1 0 does not contain 0 0. Also 0 1 does not contain 0 0. So C cross C is not integral domain because this does not contain zero divisor. So this is an integral domain but not filled. This is also wrong option. Option 3 imply not integral domain but 0 as an nilpotent element. Not integral domain, this is right. Here 0 is only nilpotent element. To prove nilpotent element, let Px plus ideal generated by x to the power 4 plus 4 belongs to Rx modulo x to the power 4 plus 4. Then that be the nilpotent element. Since this is the nilpotent element, so Px plus ideal generated by x to the power 4 plus 4 to the power k equal to 0. Here 0 means ideal generated by x to the power 4 plus 4. That imply Px to the power k plus ideal generated by x to the power 4 plus 4 equal to 0 means x to the power 4 plus 4. That imply Px to the power k belongs to x to the power 4 plus 4. And root of Px to the power k are, that imply root of Px to the power k are lambda 1 bar, lambda 2 bar. That imply P lambda 1 equal to P lambda 1 bar equal to P lambda 2 equal to P lambda 2 bar equal to 0. That imply Px belongs to ideal generated by x to the power 4 plus 4. And the element Px plus ideal generated by x to the power 4 plus 4, since Px belongs to x to the power ideal generated by x to the power 4 plus 4, this is equal to ideal generated by x to the power 4 plus 4. That means this is actually the zero element. So 0 only the nilpotent element. So option 3 is the right option. And option 4, a ring which contains non-zero nilpotent element, this is be the wrong option. Today I will stop here. In my next video, I will discuss what is the maximal ideal and prime ideal of ZX. Okay? See you soon. Stay safe and stay positive always, and don't forget to subscribe my channel for more videos. Thank you so much.